Welcome to Lesson 14, Problem 4 of Engage Math, Algebra 1. So, in this situation, we have a real world example, and we're going to use our understanding of inequalities to really better understand this real world example. So, we're going to write an inequality to represent Frankie's production constraints. Remember, C is the number of chairs that Frankie can build, T is the number of tables that Frankie builds. So, in this situation, because it takes her exactly 4 hours to build a chair and 5 hours to build the table, we're going to say 4 times every chair she builds, because C is the number of chairs she builds, plus 5, because it's 5 hours for every table. So I'm going to use T for the table variable, just as the problem says. That has to be less than or equal to the number of hours she works in a week, which is less than or equal to 40. She cannot work more than 40 hours. She can work exactly 40 hours, which is why we have the or equal to right there. Okay, part B, I've taken the liberty of already filling in the scale for you and the table and the chairs, but feel free to stop the video, try it on your own, and then make sure you agree with the way that I arranged that. Okay, now what we're going to do is we're going to say we have to take this inequality and get it into the graph. So the way that I'd like to do that is to think about our x and y intercepts. In this case, it's going to be our c and t intercepts. So if Frankie makes no chairs, only tables, what we could do is we could put 0 in for the number of chairs she makes. So then what we would have is we would just have 5t is equal to 40, because we're basically saying if she doesn't make any chairs at all and she spends 5 hours on each table she makes, she can make 5t equals 40 or t equals 8. That is the number of tables she can make, which means right here there's a point because she can make 8 tables and no chairs. All right, I'm going to get rid of that inequality or equation right there, and we're going to take the other option. We're going to figure out how many chairs she can make. So if she makes no tables at all, and it takes her 4 hours per chair and she has 40 hours, she can make a maximum of 10 chairs. So I'm going to put a point right there for the number of chairs that she can make if she makes 0 tables. So I want to take a minute and just make sure it makes sense to you why we know we have those 2 points when we graph this inequality. Okay, so now what I'm going to do is I'm going to draw the line that goes through here, connecting those 2 points. Okay, so there's our line. And what we know is that we can build any number, or not we, but Frankie can build any number, any combination of table and chairs within that 40-hour constraint, because it's not that she has to spend exactly 40 hours, as long as she spends less than or equal to 40 hours. So any of the combinations within here are going to work. So I'm just going to kind of shade that in to show that all of these points are possible combinations. Now, of course, because she can't make like a third of a chair or a fourth of a table, I mean, I guess she could, but we're not going to look at it that way. What we're going to look at it are only the integer coefficients, like the numbers that are whole numbers, 3 tables, 4 chairs, things like that. So now it says, what does the point 10, 0 represent in this situation? So the point 10, 0 is right here. I'm going to just circle it in green. And just to make sure you see, this is going to be the answer to C. So the point 10, 0 just represents the possible scenario where Frankie builds exactly 10 chairs and no tables in 1 week. This point shows just one way of the many ways that Frankie could spend 40 hours in a week. All right, so I didn't write all that out for you, but again, the answer for this is also written out in the back of your workbook. Part D. So maybe I'll write one thing down here, though. Just this is basically 10 chairs, 0 tables. But you don't have to write out that whole explanation that I just went on about. Okay, part D, it says, what do the integer points in the solution region, including on the boundary line, represent? In other words, every single red point in this graph, every single red point. So what that represents is it's the points with whole number coordinates in the solution region represent all the possible combinations of chairs and tables Frankie can build in a 40-hour week. Points on the boundary line, right on that red line, are basically represent combinations where Frankie used every one of her 40 hours. So the reason that we have all of this shaded is, let's just say we pick this point right here. So that's 2 chairs in 3 hours. Sorry, 2 chairs and 3 tables. But keep in mind, Frankie didn't use all 40 of her hours. She just worked for, whatever, 2 times, we could even see 2 times 4, 8, plus 5 times 3 or 15. So she only worked for 23 hours if this is a point that she chose for her, like how she wanted to spend her time in a given week. Any point on this line with the integer coefficients on the red line is the total of a 40-hour work week for her. Okay, this is a really important concept, so hope it all made sense, and we'll see you next time at Engage Math.